right? The other day, very strangely, I couldn't find my beta function for the non-abelian gauge series, even though it was right here. So I just didn't turn the page enough. So in Cheng and Lee, you will see that the beta function for any non-abelian gauge theory, beta g, is g cubed by 16 pi squared. I gave you the definition of the beta function. Okay, that is always fixed. We never have to do anything about that definition. That will always fix the convention for what is the beta function. It's just mu dg by d mu. Okay, that's the beta function. So this is minus 11 by 3 t2v plus 4 by 3 t2f plus 1 by 3 t2s. Okay. Now you will recall, somebody remind me what was the beta function for QED and for scalar QED. So somebody remind me QED and scalar QED so that you can compare the expression there with the expression here. Somebody tell me what is the beta function? E cubed divided by 12 pi squared. Okay, then E cubed, right? E cubed divided by 48 pi squared. So you can compare here that there's a relative factor of 4 here, 4 for the fermions compared to the scalar. Okay, so whenever you see expressions like this, you should compare it with what you already know. So in QED, so this is a 12 pi squared, this is a 48 pi squared. So this factor of 4 here accounts for that. Okay. Now this QED is a U1 gauge theory, right? It's a U1 gauge theory. What is the dimensional representations of U1? U1 has how many dimensional representations? SU2, you know, you can have a spin half, which is a two-dimensional. That's correct. So everything is, all reps are one-dimensional. All reps are one-dimensional. Okay. So here, because this is a non-abelian gauge theory, and this is SUN. Okay. So this is a non-abelian gauge theory of SUN. So why did I mention, or why did I bring up the issue of all reps being one-dimensional in the U1 case? So if it's not U1, and if it is a non-abelian gauge group with a larger Lie algebra and all that, then you have to specify what is the dimension of the representation, right? Now those of you who did this course of advanced math methods with me last year spent a lot of time on representations and dimensions of representations. Okay, so it does matter what is the dimension of the representation that you use, in which your matter is sitting. Okay, so here by matter we mean the fermionic fields, or it could be scalar matter. Okay, in contrast to, when I say matter, in contrast to what? In contrast to the gauge bosons. Okay, so any of these theories has two aspects to it. One is the gauge vector particles, and the other is the matter. And the matter typically is fermionic, but you can also have scalar particles. Okay, so it does matter, so to speak, what the matter is as far as your theory is concerned. Okay, so here it does matter what the representations are in. So it is not just saying what the representations are, but it is a certain invariant associated with that representation. Okay, so this here is what is called the quadratic Casimir of the representation. Quadratic Casimir of the representation. So in the case of SU2, there's only one quadratic Casimir, which is what? What is a quadratic Casimir of SU2? SU2 rotations. you specify representation by J, right? So what is the J squared? Is the quadratic Casimir. Why quadratic? J squared, okay? And the eigenvalue is J times J plus 1. So the value there is J times J plus 1. So there's an analog of that, which is a quadratic Casimir. It won't be just J squared, but it'll be the sum of various diagonal generators that you have, which gives rise to the quadratic Casimir of the representation, okay? So here everything was very simple, very straightforward. You didn't have to bother about what the representation is and all this sort of thing. So, but you already see here this factor of 4 that you see in the expression over there. So somebody just writes down an equation like this, you shouldn't just accept it on faith. You have to ask, what sense does each one of these terms make? Okay, and that is what I'm trying to motivate for you from your experience with QED. QED life was very simple. Everything was a one-dimensional representation. You didn't have to worry about quadratic Casimir or any such thing. And yeah, so that's what it is. So here's a quadratic Casimir of the representation. And in scalar QED, we already knew that this was a charged scalar, right? Because if it was not charged, then obviously it is not going to participate in the electromagnetic interactions. If it doesn't carry charge, it cannot interact, right? As simple as that. Okay. So what is the other key difference that you see between that expression and the expression over here? Tell me, the most, rather very important contribution that is here that is not present over there. What is the, not just negative term, but it's coming from something else, T2 of V. And what is the V here standing for? F stands for, S stands for, V stands for vector representation. And what is this? You cannot have a non-abelian gauge theory without gauge bosons self-interacting, okay? So this part is somehow fixed, whereas here you can choose the representation at will. For instance, if this was SU2, you could have a 3-dimensional representation, 5-dimensional representation, 88-dimensional representation, it doesn't matter. However, these vector will have to be in the adjoint representation. There's no other choice, okay? So this is coming from the adjoint representation, and this stands for vector, this stands for fermion, and this stands for scalar. Why was there no such contribution in the U1 case? Because the photon doesn't carry charge, whereas here the gauge bosons carry charge. So this is coming from the self-interactions, comes from the self-interactions. No, it has to. This I will explain later. When we set up a Lagrangian and we demand gauge invariance, the gauge bosons have no choice but to transform in the adjoint representation. Okay. So here for fermions, and so now we have to specify what they are in. So fermions and scalars in the fundamental representation of SUN. So they are normalized in such a way that T2 of F equals T2 of S equals 1/2. Okay. Now the other day we had that program where we did those 3 straight lines. Okay. Now I want you to look at those equations and tell me whether you're getting those equations or not. Okay, have a look at your phones and your laptop at the figure that I sent, and you reproduce for me the beta functions given in that particular notebook. So 2 volunteers, one to hold the notebook and another to write it on the blackboard. Okay, yeah, 2 of you, 1, 2. Okay. You ask one of your friends. Miss Hamsini is going to help you. Yeah. You go and tell her the beta functions, and she will have to reproduce them from this equation. While I relax for a little while. Yes. Oops. G cubed, I mean, sorry. Just my bad handwriting, that's all. Hmm? Yes, yeah. Yeah, but there are three different cases. There's a U1 coupling, then there's an SU2 coupling, there's an SU3 coupling. So I want you to get all three of them. Okay. So only when you do this, you will figure out what is what. Okay. So which one are you doing now? U1. Okay, fine. So you just put a 1 then. Okay, fine, U1. Very good. No, so the U1 there's no self coupling. So that's not there. So you can erase the first thing. First you write down the equation and let's see what is what. Whatever is given there. No, I meant you copy the three equations first and let's see how you get them. Whatever is there, that's right. Yeah. So that you know what is what. Okay. Four by 3 times 3 plus say I'm forcing you to do all these things because if I just send you this, you people never do it. Okay, now you please explain to us what is what. I meant only the beta function part, but it's okay. Now you have written the full equation, which is also fine. Okay, so please explain what is what. 4 by 3 times 3. Why 3? So that is a U1, which is not U1 electromagnetism, but this is in the standard model. Okay. So SU2 cross this U1, one linear combination of that is the electromagnetic part. Okay. Yeah. So in fact, you will see that there is a funny factor of 3 by 5. So if you take 5 by 3 times 58.83, somebody do it. Please write down 5 times 58 divided by 3 plus 29 point whatever, and tell me what you get. Yeah, that number, those two numbers there. Not that high. How much is it? 126. What was this number 126? The other day also we got this number. So this is the value of 1 by alpha electromagnetism at the Z peak. Okay. So that is what has been input into this, but there is this funny factor of 3 by 5 because this thing, this SU3 cross SU2 cross U1 is embedded in an SU5 grand unified model. So that is what fixes this normalization. Okay. So that's what you have to understand from this relation, that it is still related to electromagnetism, but through this funny factor of 5 by 3. Not funny, it's a group theoretic factor which arises when you use grand unification. Okay. Now let's go to the beta function and you explain to me what is what. The first U1, you explain to me what are the various contributions there. 4 by 3 is what we have over there in the parent equation. Yeah, that is only a half, but there are 6 fermions, right? So that comes from the number of generations divided by 2. The 2 here, this T2F T2S equals half, and then the number of fermions is 6. Exactly. So that's where that is coming from. And where is this 5 by 18 coming from? There's obviously some scalar sector in the theory, which is what, through spontaneous symmetry breaking, breaks SU2 cross U1 down to U1 electromagnetism. Okay, there is a certain scalar sector of the theory which makes a contribution to the beta functions. It makes a contribution to the beta function of both the U1 as well as the SU2. Okay, so that is why you see 5 by 18. And you also see one other factor, which is that 1 by 6. Okay. In the next line, you explain to me what are the various contributions there. Very good. Yeah. It's still the same. It's the same. Yeah. It has. Yeah. Because the way in which it contributes to the U1 coupling is different from the way in which it contributes to. This formula here is only for non-abelian theories. Okay. So it is, yeah, but it looks similar, but the actual factors have to be computed. Yeah, you see, so it depends on what representation and how many such scalars are there. It's not like there's only one scalar. There's more than one scalar, right? Because the way in which and it's also embedded in SU5. So that's why it's complicated and it has to be calculated. It's not that straightforward. Okay, now you explain to me the SU3. Very good. Why? Exactly, that scalar sector does not have any SU3 color charges, so it cannot contribute. So when you see an equation like this, you have to think about every single term that comes, and you have to think about every single sign also that you get. Okay, so it looks like a very innocent equation, 3 straight lines, but there is Physics funda. It's just the normalization. It has to do with this log over here, because the way in which we wrote it was log of m2 by m1 squared, something like this. You have to check. No? That's right. Yeah. Yeah. Exactly. So you have to check, I mean, I have given you these equations, I have given you a Mathematica program. You have to go back and see where all this is coming from. Okay. So that's the challenge, so to speak. So that is the story of the beta function. So if somebody asks you what is a beta function, you had better know all this by now. Also,
Breaking into these SU5 gradual matrices, they don't understand that.
yeah, not really. It's an advanced topic. It's in the BSN course. Okay, this is given as an example of beta function calculations. Okay, now if you have an SU3 and an SU2 cross U1, which are just a direct product with no connection between any one of them, then you don't know what their relative normalizations are. But supposing these three are sitting in some unified picture, and then they are born out of a common mother, so to speak, then their relative generators will enjoy some relations between them. Okay. Now, if you say that all this came from an SU5 unification, then in the SU5, you do not have any arbitrary factor in the normalization of the generators. Supposing it had been SU4 cross U1, okay, then that U1 is not talking to the SU4 part, but if the whole thing is sitting inside a semi-simple Lie group like that, then there all of them are mutually related to one another. Okay, that's the only way I can express it. So it is a hypothesis that maybe they came from an SU5, in which case this factor of 3 by 5 you need in order to get this particular normalization. Okay. Very good question. You tell me, where is it coming from? What is the relationship between SU2 and U1 gauge couplings? How are they related to each other? There's the sine squared theta w, right, which is experimentally known. Okay, so from the experimental value, this is what you Google that article by Utpal Sarkar, the one that I gave you a reference to. Google it, and then you can see the relations. And since you've asked me so many questions, now you have to go and do it on the blackboard. Okay. See, this is the trouble. If you ask questions, then you have to go to the blackboard and answer them. Yeah.
It can be in any representation.
It's chosen to be. Yeah. You can make them. Yes. Yeah. But the fermions, we know that the quarks transform in the three-dimensional representation of SU3. We know that the neutrino and the electron, they transform in the two-dimensional representation of SU2. So these are phenomenologically known. The scalar sector is motivated by spontaneous symmetry breaking. But today we also know that to get the Higgs mass and those relations correctly, you have to choose it in a small, like a doublet and so on. So there's always experimental or observational information which is guiding you in that way. Okay. Okay, did you find it? Why not? Yeah, I gave you the reference. Look for Sarkar. Search SARKAR. Right. Now you please look at that PDF, and then you give me the relations, and then you tell me how you got those numbers. Right. Good. Download PDF. Now you ask one of your friends to come and help you with this, how he got these numbers. Assuming you have friends, of course. I have only enemies, so I can't say I have any friends. Okay. Okay, go and write down those on the blackboard and get those numbers. There is no 3 by 5 there. Yeah. You see? This is the important thing. Yeah. No, no. How can it be alpha? Okay. No, is it? Alpha S inverse. Yeah.
EM, okay.
Yeah. EM stands for? Very good. Yeah. By now you should know what is sine squared theta w. But anyway, if you don't, this is an opportunity to learn. Yeah. See, these are all important things to know. Alpha 3 is still quite large. It's about 0.1 or 0.12. Okay. Okay. Fine. Now you plug it in and see whether you get those answers. Come. Plug it in.
They're getting the correct number.
You only wrote sine squared theta w. What is cosine squared theta w? You don't say. Okay. Good. See, unless I force you like this to come to the blackboard and write these things, this is what happens. Right.
The calculator it's coming 59.18.
Yeah, you have to take that. Okay, folks. So this is a short story made very long, but it's important to have an illustration and to know all these numbers. Okay, you have to know these numbers like this 1 by 127 at this. Can't just say 1 by 137. That's only in the Thomson limit. Okay. At electroweak scale, it is different. It has grown by about 7-8%. It's not a small change. And you have to know the value of sine squared theta w, which is this. And when these things have not changed much, I mean, the values that we have from the 1970s or so is still the same today. So these are numbers that you should just commit to memory. Okay. Okay, so good. So we got some on-hands practice with this particular thing. So where was I? What did we do in the last class? We had written down the Rosenbluth formula, right? That's more or less where we stopped. And then I was going to tell you about the Feynman rules for, where did I stop? You remember? I said K1 and K2 in terms of even for a point charge, right? Is that what we did? Okay, so we also need to know what are the Feynman rules for quantum chromodynamics. QCD. So just like you have QED, which is for charged particles with an electric with a photon. So QCD is the interaction of colored particles. By the way, this is only a name, okay? There is no other significance to this name, color. It's just a name. There's nothing to do with the color that we see with our eyes. There's nothing to do with the electromagnetic spectrum. It is just a name. But it is useful because it's like with light and what our eyes see, colors as a mixture of three primary colors, okay? So it's like that. So there are three primary colors in QCD, which are given the names R, B, G, and then you white it out, and whatever you see in nature, color singlets are white objects because the R, B, G gets whited out, okay? It's not the white that you see with your eyes, but it's an abstract white. Okay, colored particles with gluons, but the difference is that these gluons also carry both color and anticolor, color and anticolor. Since you asked me about that joint representation, let me ask you, in the SU2 case, how do you know how to define the three generators? Okay, let's call them JI like this. Okay. How about, so how many JI are there in SU2? Three of them. I equals 1, 2, 3. Okay, JI, JJ. Commutator is JK like that, and epsilon I JK like this. You all know this. What about then? I, J, K. No, I didn't understand. Not iota, I. This is not the Greek iota, it's the Latin I. Oh, you want an I over here like this. Not iota. Iota is Greek. I is Latin. Okay, it's the Latin I, not the Greek iota. Not that I don't know how to say iota, but it's not iota, it's I. Okay. Like everybody says Levi Civita. Even I know how to say Levi Civita, but his name was Levi Civita. Okay, so you can't call him something else. You can't take my name Anant and call me Anand, right? Although Anand is a good friend of mine, I'm not Anand. So Levi Civita. Okay, fine. So here, let me ask you, if I want to construct 3 by 3 matrices, 3 by 3 matrices, if I want to build out of these, call them Ti, and the jkth element of Ti, supposing I say that this is epsilon I jk, supposing with an I, since you people seem to like I, and I ask you to construct T1, T2, T3. Can you please do it for me? Okay. So today I'm in the mood of making you people come to the blackboard and do it. Here. Write T1 and write down the elements using that formula. Okay. Let's get into the I. Later we'll add the I if needed. I think we will need it. Let's keep it. Otherwise we will not get the, yeah. So there are 3 of them, and each of these is now a 3 by 3 matrix. Okay, so let's write down the elements. No. Write a 3 by 3 matrix. Erase this. Write a 3 by 3 matrix for T1, whose jkth element is given by T1 JK. Okay. No. Okay, fine. You want the I. Very good. Yeah. No. You cannot have a 1 1 element. Very good. Yes. Yes. 2 3. Very good. Yes. Yeah. Okay. Then T2. All the diagonal elements have to be 0. There is no option. Because this is Levi-Civita is totally antisymmetric. Excellent. Yeah. Antisymmetric, no? Just from that itself we can, no, antisymmetric. Ah, yeah. Very good. So these are the explicit matrices, and these matrices also satisfy the same algebra. So Ti, Tj is I epsilon, Ijk, Tk. Okay. So this has the same structure as the defining algebra, satisfies the same algebra. So these objects therefore furnish a representation of the algebra, right? What kind of representation is this? This is the adjoint representation because it is cooked up from the structure constants itself. Okay? Supposing this had been SU3, how many such generators do you have in SU3? 8. So you can build 8 by 8 matrices which will satisfy the same algebra, and that is the adjoint representation of SU3. Okay, and the transformation law for gauge bosons is something that has a transformation law that looks like this, and that's the reason why they have to be in the adjoint representation of the gauge group. Okay, but because it is done in this particular way, it is cooked up from the original matrices themselves, and in the case of SU3 you have a 3 and a 3 bar, and by considering the tensor product of 3 times 3 bar you get a 1 plus an 8. So the 8 is already the adjoint representation because it's transforming like the adjoint representation, but it's cooked up from both the fundamental and the anti-fundamental representations. So that's the reason why the gluons have to carry color and anti-color. Okay, because they come from the 3 times 3 bar, which is equal to a 1 plus an 8 for the case of SU3. So this is a 3 bar times a 3 is this plus this. So this is a 1, and this is a 3 times 4 times 2 divided by 3 equals 8. Okay, so it is coming from a 3 and a 3 bar, and that's why the gluons which are in the adjoint have to carry both color and anti-color. So if you have quarks which carry, so these are called quarks, of course. So let them carry RBG, and they can be represented by 3 column vectors like this: 0 1 0 and 0 0 1. Okay, so this is a way in which you represent quarks of R, B, and G. R is being a 1 here, B as a 1 here, G. This is just a choice of an explicit representation for the 3 vectors that would define define colors. So then we need to have something that also defines gluons. Okay. Now, please help me with this. How would I be able to cook up states and get quark-antiquark or color-anticolor quantum numbers to define various gluonic states? So, how many such gluonic states do I need? Okay, 1, 2, 3. Because it's already whited out. Okay. Besides, in SU3, the adjoint representation is 8-dimensional. So when you get this 3 times 3 bar, so please tell me how to white out using R, B, and G. How to get it to be whited out. Thanks. Excellent. Divided by √2. Okay. So that is the singlet, and we don't care about this because no singlet gluon exists. No singlet gluon. Now all this is clear now in the year 2025, but when people started doing these things, of course, they were struggling with all these things and figuring out what is what. This theory is now a little more than 50 years old. Okay. It's not that old. Okay. Yeah. I don't know. Yeah, it's a good project for summer. Okay. After we are done with modular forms. Okay. Not necessarily this summer, next summer, 2028, so many years, 2040, RB bar plus BR bar by √2. So these are the choices. Now nobody has to agree with these choices, but this is a particular choice and convention that is used by authors. RR bar minus BB bar by √2, RG bar plus GR bar by √2, and 5 obtained by various permutations minus RG bar √2. So since Mr. Kanishka had asked me about explicit color quantum numbers, so बस आपकी फरमाइश G bar G2 RR bar. This is an interesting one. BB bar minus 2 GG bar by 2. Why does this thing look like this? Look at this quickly and tell me why do you think this looks like this? What is that? One of the Gell-Mann matrices. So that's where this thing is coming. Such algebra is also used in the context of the SU3 flavor with pseudo scalar mesons. It's the same mathematical structure. Okay, here this is a gauge symmetry. The SU3 flavor is a global symmetry which has nothing to do with this SU3, but just that the symmetry happens to be SU3 there and it happens to be SU3 over here. Okay. Yes. So you yes, it does. And that's the other screenshot that I sent you, which you may have seen. It has all these Gell-Mann matrices, very nice. And I compute all these things given in the book of Griffiths. Okay. So let's do that. Somebody please share um, on Teams. Now you're also been added to Teams. So you can share the book of Griffiths and let us see what are the things that that particular notebook has done. Okay. Now remember that in the analog of the Coulomb potential that we wrote down for the Charmonium system, there was a minus 4/3, and I said that this is a color factor. So that factor comes from the computation of all these things, which is what is done in that second screenshot that I sent you. Actually, that was the first screenshot that I sent you. I did all those calculations to reproduce the results from Griffiths. Okay, so Mr. Chug is going to share the Griffiths book, and then you're going to see what are all the things that are done in that screenshot, and one of you will now write a notebook to reproduce it. Okay. So it comes from including these color factors and then calculating them and getting them for the various combinations, which are called octet, singlet, triplet, and sextet. All of them are calculated. Okay. Which formula are you looking for? If you see that screenshot, the equation numbers are mentioned there. You see? So you have to go and check what the equation numbers are and what I have done in this notebook. Rest of this class today we will do that. Yeah, hello. Yeah. Yeah, good morning. No, I'm not interested. Did you find the equation number? Are you sharing on Teams? Are you people able to see? Yeah. Which book is this? This is a second revised edition. Go to page 1. No, is this a second revised edition or not? Go to the cover page, please. No, this is not the second revised edition. So can you get it from LiveGen? Who's got the second revised? Yeah, okay. So Mr. Kanishka is going to share. You're named after an Air India flight. There used to be one Kanishka. I know. Yeah. There's also a king, I guess. Yes, yes. Yeah, okay. Okay, so please look at that notebook and see what are all the factors that I have calculated for you and how. Okay, one of you go to the blackboard and write down what are all the factors I have calculated and let us compare it with what we have. Okay, blackboard, folks. Yeah. Quark-antiquark gives rise to, quark and quark gives rise to triplet and sextet. Why? Quark times quark. Q times Q is a 3 times 3, right? So let's draw two boxes like this, equals this plus this, right? What is this? 3, 3. This is it's 3 only, it's a 3 bar, see over here. And this thing here, 3 times 4 divided by 2, which is 6. So quark times antiquark is this only. We already know that there's a singlet and then there's an octet, whereas a quark times quark has to give you a triplet and a sextet. Okay, this is just young tableau calculation. So we had to calculate the color factors after doing all the traces for each one of these combinations, and the way you do it is by using the Feynman rules and evaluating those traces, which is what is done in that particular notebook. Okay, what are all the factors that have been computed there? So Mr. Chaitanya is going to write this for us. Mr. Bhatt rather is going to write down all these things. What are all the answers? This is not stuff that can be explained at the blackboard. You have to do it on hands. There's no other way. Okay? How about one of you writing a notebook to reproduce what I have done? Can one of you write a notebook to do that? I mean, you just have to see what I've done and you do the same thing. But I'll tell you a secret if you don't tell anybody about it. I stole those Gell-Mann matrices from the internet. How did I do that? I typed on Google Gell-Mann matrices Mathematica. There's a guy who has a notebook over there and it says download notebook. And I downloaded the notebook and I cut and pasted. So do it. हाँ, गूगल खोलिए, गूगल में तलाश कीजिए Gell-Mann मैट्रिक्स मैथमेटिका. Right, Math World, yes. Download notebook. हाँ, खोलिए और इसको कट और पेस्ट कीजिए. नाम बेचारे जी का भी छोड़ना नहीं. नया नोटबुक खोलिए. फाइन कैल्क की ज़रूरत नहीं है, ये बहुत बड़ा नाम है, इसीलिए इसका नाम हम GM बना दिए. अपनी मर्जी, अपने नाम से भी कर सकते हैं. हाँ, अब देखिए क्या किया हुआ है उसमें. ये सब इसकी ज़रूरत नहीं है. No, this I was only checking that it's normalized, but it's okay, you check it. I'm just checking that this thing is normalized correctly. Okay. and it is no problem. Okay. Then for each one of the combinations, you have to evaluate these traces. And it is given in the book of Griffiths, but he does it in a fairly complicated way, of course, because he wants to explain every step. Whereas what I have done is I have just used the algebra and I have used these definitions in order to get the answer. Yeah, you just write down the numbers that you get from the notebook. Just make a list of the numbers that I have given for each one of those. All the quantities of interest. Okay. Yeah. And that corresponds to which configuration? I must have written there. Rather, it must be there in the book of Griffiths what it corresponds to. Oh. Yeah, yeah. Okay. Bring your iPad. You can have a look. So there's 4 of them. There is a triplet, there's a sextet, there's an octet, there's a singlet. So you have to do the algebra for each one of them using the Gell-Mann matrices, and you get the 4 numbers. So in Griffiths, he takes a couple of pages to explain every single thing, whereas here, if you wrote a Mathematica program, you can straight away get the answers. Okay, and that's the purpose of this particular exercise. And it is not something that I can explain on the blackboard. Okay, you have to take out Griffiths, you have to read those exercises, what it is that he's doing, and you do on hands. You have to type your Gell-Mann matrices, or steal them, or cut and paste them, or do whatever, and just do it, then you'll get the answer. Okay, Mr. Kanishka is doing it for you, and now he is going to send you a copy of the notebook when he is done, right? And how long is it going to take you to do it? It all depends on how nice you are to them and how nice they are to you. Yeah. I also have the notebook, but I'm not going to send it to you. At least one of them you can do, no? The simple one you can do. That's a complicated one. You do the simple one.
Square bracket and these two are bracket.
No, they're all braces. So the Mathematica convention is that brace is used to define matrices and column vectors and so on. Okay. Now you have to figure this out for yourself, no? And why is this looking like this? This is 2 open brackets, is it? Yeah. Okay. So you have to do it for each one of them, for the R, for the B, and then for the G. Okay, that is what is being done. I think you have to check what is being done. Okay, thanks. I'll give a summary of what are the calculations. After introducing the Feynman rules, the Feynman rules will require us to introduce color vectors for each one of the colors. It will require us to introduce a symbol for each one of the gluonic states. Those are called A in the book of Griffiths, whereas these things are called C for the color and A for the gluons. Okay. Now we are well over halfway in this course, and I still have no idea if people are following anything that I'm saying or not. Are you people following anything that I'm saying? Following something? Anything? Nothing? I'll I'll give you three possibilities: R, B, G. Something, anything, nothing. Which? Well, now I've forgotten what is B. Yeah, she's following something. Yeah, but you have to sit down and do it. Okay, just put pencil to paper. No, have to do these calculations. So there are these additional factors that we need. So if you look at the quark and anti-quark, you get an octet and singlet. Octet and singlet. So this is to get the static interaction between Q and Q bar. Static interaction between Q and Q bar. Give me an example of a static interaction between Q and Q bar. Let's say that there's a one gluon exchange in quark and anti-quark. Give me a physical example of a static example of a quark and anti-quark. Charmonium, bottomonium, right? See, you missed all those classes. So, charmonium, bottomonium, okay? In those cases, these are the two sources of color, Q bar, the exchange of a quark. And we are asking what is the potential between them. And it does matter whether the overall state is in an octet configuration or whether it is in a singlet contribution of color, okay? So here, if you work out F octet, after doing all these traces, which is what we have done in the notebook, you will get -1/6. So this, all this is to answer the question of Mr. Kanishka, who was asking, when do we ever do these color indices and all? This is an example. And here comes the answer for the singlet. It is 4/3. Okay. So that is where this is coming. Very good. Yeah. So all of you download it and then you work out all the examples, not just the simple one. So here this is an example. So this is charmonium, bottomonium. Charmonium, bottomonium. And that's why you get the potential -4/3 times alpha S divided by R. Okay, this is where this is. What about quark-quark? Give me an example of a quark-quark interaction. Well, inside a proton, you have quarks, right? So there's a pairwise quark-quark interaction, okay? And these are in configurations of triplet, and F is in a contribution of a sextet. And this factor, after doing all these things, if you work it out, triplet will give a -2/3. No, you give a +2/3. No, -2/3, and sextet gives a 1/3. But there's no quark-quark bound system. It's 3 quarks you need in order to do that. And so this is how it will play a role, that this thing then has to be combined with this quark in order to get a Q bound state. There's no class on Thursday, so you have a full week, all of you. I won't be here, so you'll have a week of peace and quiet. No pravega, no nothing. Please go and study every single thing that I have taught you so far, okay? 1 week, okay? There's a word only in Urdu, it's called riyaz. Riyaz karni chahiye, huh? Padhai nahi, sirf riyaz. Samjhe nahi samjhe? So this has other implications also. Now I'm going to ask you people to draw me a diagram for quark-quark going to 2 gluons. Q plus Q bar going to 2 gluons. Okay. Now please draw a diagram without looking. That guy is already looking at Griffiths. No. So I'm not going to ask you. Yeah. Come. See, I have to plan my retirement. I want to become a stand-up comedian after that. When I was a kid, my parents wouldn't let me consider any such career. Now, of course, they are not there, so I can do whatever I like. Yeah. Only one? No, no, tree level. No, this also, even in E plus E minus 2 photons, this is not the only diagram. Even in Compton scattering, there are two diagrams. That's called the cross diagram. Okay, so please cross them. Cross the final states. Yeah. Not S, but T and U channels. Yeah.
You mean like this?
I don't mean, you mean. Yeah. Yeah, right. That's what you mean. Okay. So even in Compton, you have two such diagrams. There's a third diagram here, which Miss Durba has just told you. She gave you a hint. Please draw it. Very good. So QQ bar touch and produce a gluon. Q and Q bar will touch. Very good. Produce a gluon. And this gluon can then split into two gluons.
Yeah, right. Oh.
Exactly. Right. So there are three diagrams of this particular thing. And once again, you have to ask whether this overall thing is going to be in a singlet or octet. Okay. Both possibilities are there. So you have to project it onto the spin singlet state. So you can project all this onto the spin singlet state. There's a guy called Varun Grover. You know this guy? He's a stand-up comedian. Yeah, he's my role model. So he's pretty good, very popular. You heard of him? No? Anyway, he has a brother, Tarun Grover, who used to be a student here. See, one guy is a physicist, another guy is a stand-up comedian. I want to be a linear combination of both. Yeah. See, this course is so boring that occasionally we have to fool around, no? Otherwise, it's just so awful. So this you can again work out in Griffiths, and you'll find out that the matrix element has a very simple structure like this. And then there is a state. What are the various states of the Charmonium system? Please remind me. We have been looking at various figures, cross sections, all these things. What are the various states of CC bar system? Okay. J psi. You remember that one? What were its quantum numbers? It's the main production channel for E plus E minus to produce Charmonium. So if it's an E plus E minus collision, it can produce a virtual photon. And what are the quantum numbers of a photon? JP. 1 minus. No minus 1. 1 minus. So that thing becomes the J psi. It has the same quantum numbers. So the J psi has quantum numbers of 1 minus. Okay. So that's not what we are looking at, but we would rather look at another state, which is a spin singlet. What is the name that we gave it? Please look at your Charmonium system and tell me what is the name of the Charmonium state, which is a spin singlet. 1s0, right? 1s0. So they are always given the name eta, okay? Eta C. So eta C can go into what in the final state? What does the J psi go to? Remember, I have been screaming at the blackboard. The J psi is a very long-lived particle because of the OZI suppression, OZI, Okubo's Izuka suppression, which required at least 3 gluons to be produced, which then fragment and produce pions in the final state. So J psi can only go to 3 photons, whereas this thing here can go into 3 gluons. This thing can go into 2 gluons. What is the corresponding situation in positronium? Positronium ground state is a singlet state which decays into 2 photons. Okay, remember we did this calculation? No, you don't remember. We did this calculation for positronium, right? So this thing here is 8 pi by c h bar alpha s by m times. Now if this is a 1s0, then you know if it's a 1s0, the quark and antiquark touch each other. What happens when they touch each other? Quark and antiquark touch each other. Oof, they can go into energy. And what kind of energy? Can it produce 1 photon? Can it produce 1 photon? No, because momentum is not conserved, it will produce. So it has to produce at least 2 photons. Okay, so this is the favored. But what do I mean by saying that they touch each other? That means that the wave function at the origin is not equal to 0. And this particular rate must involve the value of the wave function squared at the origin, right? There's no heuristic way of looking at it. This means that there's an effective potential that is generated by one gluon exchange. Then it becomes a non-relativistic system. It's a hydrogenic system where you can arrange its states in a spectroscopic manner, and then so the Feynman diagrams are now thrown away. Okay, so now it's like positronium. It's just a quantum mechanical non-relativistic system. Okay, however, it must still involve the strong coupling constant. Okay, that there is no escape. So this thing squared actually. So Feynman diagram is gone, and this is what is done in order to get this matrix element which has gone here. Okay, so the non-relativistic part is what gives you this alpha s. Okay, this is the matrix element for this particular. जाके थोड़ा रियाज करनी होगी, ठीक है? ग्रिफिथ से और कुछ नहीं. See, sometimes I know many years ago when I was a chairman, luckily I'm not, I got so bored of my own speeches that I decided to give it in Hindi. Okay, welcome address. So later one student came and told me, I'm very happy you spoke to me, because if you had spoken to me in English, I wouldn't have understood anything that you said. So in a country like ours with a lot of diversity, sometimes language can also be an issue. So if you have any difficulties, please let me know. Of course, I can try to speak to you in Tamil also, but then probably I'll be the only guy who understands what I'm saying. Yeah. Okay. But my Bangla has improved recently because we have a neighbor who had a big fight with his sister on Sunday. For over 2 hours, they were shouting at each other in Bangla. My Bangla improved thanks to this. Good. So this can also decay into 2 photons. This eta C can also decay into 2 photons, and it can decay into 2 gluons. And this is a test of QCD, because it will be 8 by 9 times alpha squared by alpha s squared. Okay. So this is a test of QCD. I think this is a bunch of things that there is more new stuff that I can start with, but I don't want to do that. I think I'll stop here, and you people have to catch up with this, otherwise there's no point in my going on talking. Okay, so I stop here. We meet again on Tuesday. You have 1 week to make up everything that we have studied so far. All right, any questions?
pi plus pi naught and pi minus. So
Yeah.
restricted and eta was one thing.
Yes.
But usually what happens for spin and other things that these things are totally symmetric and this is
Yeah.
in this case in this structure was E bar plus
Right.
so this is seamless become
I think it has to do with the fact that these are pseudoscalars. Okay. So it's also the somehow the parity, but I'll check and let you know why it is the case. Probably in Griffiths, he has discussed the same chapter, chapter 8, has a long discussion on all these light mesons. So you can have a look there and see if the answer is there. Anything more? Okay. Stop recording.